Imagine for a moment that you step outside tonight.
Okay.
Maybe you're walking the dog or you're just taking the trash out. It's a crisp, clear winter evening. You look up toward the south, catching that familiar rectangle of stars that makes up the body of Orion the Hunter.
A very familiar sight for anyone in the northern hemisphere this time of year.
Right. You see the three stars of the belt, Rigel blazing blue down at the foot, and then you look up to the left shoulder, expecting to see that deep orange-red glow of Betelgeuse.
But tonight, the shoulder isn't just glowing, it is screaming.
Exactly. It's not a star anymore, it's a beacon. It's shining with an intensity that physically hurts your eyes to look at directly. It's casting these razor-sharp, weird shadows against the pavement. It's washing out the rest of the stars. It is piercing through the atmosphere like a welder's torch suspended in the sky.
What you were describing is the single most violent, transformative event that can happen in the universe. A Type 2 supernova. And if that happened to Betelgeuse tonight, it would be the kind of astronomical event that defines a civilization. It takes the slow geological timescale of the cosmos and suddenly accelerates it into something human, immediate, and frankly, terrifying for anyone who doesn't understand what they're looking at.
And that is exactly what we are unpacking today. We are doing a deep dive on a scenario that has captivated humanity for centuries, but really ramped up in the public consciousness over the last few years.
It definitely has.
We are asking the question, what happens if Betelgeuse exploded tonight? And I want to be incredibly clear right off the bat so you know what you're getting into. We aren't doing the Hollywood disaster movie version today.
No, we are sticking to the hard astrophysics.
Exactly. We are looking at the actual science.
Because when you hear the word supernova,
Yeah.
the immediate association is apocalypse. It's the end of the world.
Right. Boiling oceans and ozone depletion.
Exactly. But the reality is far more nuanced and honestly, far more fascinating. Our mission today is to walk through the timeline of this stellar death, minute by minute, from the invisible signals deep underground to the visual spectacle above, and answer the big questions.
Like, is Earth safe? Could we see it during the day?
Right. And what does this say about the life cycle of the universe as a whole?
To do this, we've got a massive stack of research to get through today. We're pulling data from Universe Today regarding those mysterious dimming events that freaked everyone out a few years ago.
Those were highly misunderstood events.
Yeah, they really were. We're also using detailed mechanics of stellar collapse from Astronomy magazine and Lumen Learning, and some really thoroughly researched papers from the Arxiv preprint server regarding cosmic ray impacts and atmospheric chemistry.
It's a heavy stack. But it's a story worth telling properly, with all the rigor it deserves.
So settle in. We are about to watch a star die.
And in doing so, we might just learn how we came to be alive in the first place.
Let's start with the hook. Let's set the scene properly, because the absolutely fascinating thing I learned while prepping for this deep dive is that if Betelgeuse blew up right this second, we wouldn't look up and see it.
Not immediately, no.
The light isn't the first thing to arrive, which seems completely counterintuitive to everything we're taught about space.
It is counterintuitive. We're so used to light being the absolute fastest thing in the universe, which it is in a vacuum.
Right.
But inside a dying star, light is actually trapped. If Betelgeuse were to go supernova right now, the first warning wouldn't come from a telescope. It wouldn't come from an amateur astronomer in their backyard looking at Orion.
So where does it come from?
It would come from deep, deep underground.
We're talking about the neutrino detectors.
Precisely. We're talking about facilities like Superkamiko Kande in Japan or the Ice Cube Neutrino Observatory buried in the Antarctic ice. Have you ever seen photos of the Supercave facility?
Yeah, I have. It looks like a set from a science fiction film. It's this massive, cavernous tank of water buried under a mountain, and it's lined with thousands of these intricate golden glass bulbs.
Right, those are the photomultiplier tubes. That specific tank holds 50,000 tons of ultra-pure water, and it's buried a full kilometer underground for a very specific reason, to shield it from normal, everyday background radiation like cosmic rays that hit the Earth all the time.
So they are down there in the dark looking for neutrinos.
Yes. These are often called ghost particles. They have almost zero mass, they carry no electric charge, and they almost never interact with normal matter.
I remember reading that billions of neutrinos pass through my fingernail every single second, mostly coming from our sun, and I don't feel a thing. They just pass right through me.
Exactly. To a neutrino, the Earth is basically completely transparent. They fly right through the planet without hitting a single atom.
But they do hit things occasionally, right? That's why we build the detectors.
Right. If you have enough ultra-pure water and enough incredibly sensitive sensors, every once in a long while, a neutrino will crash dead-on into an atomic nucleus in that water.
And what happens then?
It creates a tiny, incredibly brief flash of blue light called Cherenkov radiation. It's essentially an optical sonic boom. That's what Superkamiokande is watching for.
So bring this back to Betelgeuse for us. The core of the star collapses. What happens to the neutrinos?
When the core of a massive star like Betelgeuse collapses, the pressure and temperature reach levels that defy human comprehension. The protons and electrons in the core are violently crushed together to form neutrons.
Just a massive squeeze.
Yes, and this process called neutronization releases a pulse of neutrinos that is simply unfathomable. We were talking about 10 to the power of 58 neutrinos released in a fraction of a second.
10 to the 58th power. I mean, that's a 1 with 58 zeros after it. That's a number that doesn't even register in the human brain.
It really doesn't. It's a quantity that exceeds the number of atoms in the entire Earth by a vast, vast margin. It's a literal tsunami of ghost particles.
Oh.
And here's the crucial part. Because they don't interact with the outer layers of the star, they don't get stuck in the explosion.
Oh, I see.
They fly straight out of the core, completely ignoring the millions of miles of stellar gas surrounding them, traveling at essentially the speed of light.
Meanwhile, the light, the actual photons that we would see with our eyes, is stuck inside the traffic jam of the exploding star.
That's a brilliant analogy, yes.
Yeah.
The physical shock wave and the photons are trying to push their way through the incredibly dense, heavy, opaque layers of the star's hydrogen envelope.
And that takes time.
A lot of time. Depending on the density models for Betelgeuse, which varies very slightly, you could take 3, 4, maybe even up to 10 hours for that shock wave to finally break the surface.
But the neutrinos.
The neutrinos have a clear highway. They get a massive head start.
So the realistic scenario plays out like this. It's, say, 2 in the morning on Earth. The computers at Superkamiokande and the detectors under the ice in Antarctica and the ones deep in the mines in North America all suddenly light up.
And we are not talking about a subtle blip. It would be a massive, undeniable spike in the data. We actually have an international protocol for this called SNUWS, the Supernova Early Warning System.
How does that work?
It's an automated network connecting these detectors globally. It's designed to triangulate a burst just like this. If these detectors all register a massive neutrino burst within seconds of each other, the central server algorithms realize instantly, okay, this isn't random thermal noise, this isn't a glitch in the software, something huge just died in our cosmic neighborhood.
And nearby in galactic terms is relative, of course, but given the sheer intensity of the burst, they'd know it was Betelgeuse.
They would almost certainly suspect it immediately. The intensity of the neutrino flux would be far higher than anything we've ever seen. So an automated high-priority alert goes out to astronomers globally.
It would probably say something like, neutrino burst detected, direction Orion, get your telescopes ready.
Exactly.
That is just such a cinematic image to me. The entire global astronomical community knowing with absolute data-driven certainty that the sky is about to permanently change, but having to literally just sit there and wait that 3 or 4 hours for the light to catch up, it's the ultimate suspense.
It really is. It's the universe giving us a countdown timer. And when that wait is finally over, that's when we get what astrophysicists call the shock breakout.
Walk us through that exact moment. What does the shock breakout look like?
It wouldn't be a slow, gentle fade-in. It would be a violent, utterly sudden brightening. The shock wave from the collapsed core finally punches through the surface, the photosphere of the star.
The surface just erupts.
Right. The temperature of the surface spikes from a relatively cool 3,500 Kelvin to hundreds of thousands of degrees in a matter of seconds. In the constellation Orion, that left shoulder would suddenly flare up, potentially brightening by a factor of thousands in a very, very short window.
And that brings us to the immediate human reaction. Because if I'm just a regular person walking the dog and I see a star suddenly get brighter than the moon, my lizard brain goes straight to panic mode.
It's a completely natural response to something that violates our understanding of the permanent night sky.
The questions that would flood social media, the news networks, they are obvious. Is this the end of the world? Are we in danger? Are we in the kill zone?
That is the primal fear. And we really should address it right up front based on the physics and the consensus in the field, including the analysis from the Mellett and Thomas paper on atmospheric impacts.
So what's the bottom line?
The short answer is an unequivocal no. We are not in the kill zone. Earth is safe.
Okay, that's a massive relief. But we need to define kill zone scientifically so you understand why we are safe. What exactly is the lethal radius of a supernova?
In astrophysics, we calculate the distance at which the initial high-energy radiation, the gamma rays and X-rays, would be intense enough to fundamentally destroy a planet's ozone layer and trigger a mass extinction.
And what is that distance?
For a standard Type 2 core collapse supernova, that distance is generally considered to be roughly within 25 to 50 light years.
So if a star exploded 30 light years away from Earth, we'd be having a very different conversation.
We'd be in profound trouble. At that range, the gamma rays would completely strip the ozone layer. This would leave the surface of the Earth entirely exposed to lethal solar ultraviolet radiation from our own sun.
It would essentially sterilize the surface.
It would likely collapse the planetary biosphere. In fact, there's actual evidence in the geological record, which is referenced in some of our source material, that a nearby supernova about 2.6 million years ago, at a distance of maybe 150 light years, might have contributed to a minor extinction event of marine megafauna.
What, Betelgeuse isn't 50 light years away?
No, it is nowhere near that close. Pinning down the exact distance to Betelgeuse has historically been notoriously tricky because the star is so massive and diffuse, its edges are fuzzy. But the best modern estimates, using incredibly precise parallax data from the Gaia Space Observatory and combined with radio observations, put it somewhere between 640 and 724 light years away.
So even at the absolute closest estimate, we are more than 10 times the safe distance.
Exactly. That 600-plus light-year buffer is enormous. And this comes down to the inverse square law of radiation.
Can you explain the inverse square law simply?
Sure. It means that as radiation travels outward, it spreads over a larger and larger sphere. So if you double the distance from the source, the intensity of the radiation doesn't just cut in half, it drops to 1/4.
Oh, wow. So it drops off very fast.
Very fast. By the time the high-energy radiation reaches us from 600 light years out, it is so profoundly diluted that it poses no threat to human life or the biosphere.
So it truly is a spectacular show, not a physical threat. It's a scenario of absolute awe, not danger.
Precisely. It's a front-row seat to the ultimate cosmic fireworks display, but we're sitting safely behind a massive 600 light-year blast shield.
Before we get into the specifics of what that light show looks like from the ground, I want to step back and talk about the star itself. Because to really understand the mechanics of the explosion, we have to understand the victim. What exactly is Betelgeuse? I know everyone says it's big, but the word big doesn't really do the physics justice.
Big is a massive understatement. Betelgeuse is a red supergiant of spectral type M. Now, let's unpack that terminology.
Yeah, do it.
In astronomy, stars are classified by letters O, B, A, F, G, K, M, which tells us about their surface temperature.
O stars are the incredibly hot blue ones, right?
Yes, the hottest and most massive. And M stars, at the other end of the spectrum, are the coolest, glowing a deep reddish orange.
Just for context, our sun is a G star, correct? Sort of yellow-white and medium temperature.
Correct. Betelgeuse has a surface temperature of only about 3,500 Kelvin, which is relatively cool for a star. Our sun is closer to 5,800 Kelvin. But what Betelgeuse lacks in surface heat, it more than makes up for in sheer terrifying volume.
I absolutely love the solar system comparison for this. If we magically dropped Betelgeuse into the center of our solar system, replacing the sun, where does the physical surface of the star end?
If you put the center of Betelgeuse where the sun is right now, its surface wouldn't just swallow Mercury and Venus. It wouldn't just swallow Earth and Mars.
That's already mind-blowing.
It gets crazier. The surface of the star would extend out nearly to the orbit of Jupiter.
That is absolutely staggering. You're talking about a single physical object that spans hundreds of millions of kilometers.
It is, and yet, and this is the part that always fascinates me from a physics standpoint, it has a mass of only about 15 to 20 times that of our sun.
Wait, hold on. So it's millions of times the volume of the sun, but only 20 times the mass. How does that work?
It means its overall density is incredibly low. Astronomers often describe red supergiants as a red-hot vacuum.
A vacuum?
Yes. The outer layers of Betelgeuse are thousands of times thinner than the air we are breathing right now in this room. It's essentially this ghostly, billowing, unstable cloud of glowing gas, tenuously held together by a tiny, incredibly dense gravitational center that is actively struggling to keep control of the whole structure.
And we know for a fact it's unstable. I remember clearly back in late 2019 and early 2020, there was this massive global news cycle about what they called the Great Dimming. The star dropped significantly in brightness, visibly so to the naked eye. Everyone, myself included, thought, well, this is it. It's shrinking right before the boom.
That was such a fascinating moment for stellar physics, and the Universe Today source breaks this down beautifully. For a few months, the headlines were literally screaming that a supernova was imminent,
I remember.
but the scientific community was really deeply investigating it. Was the star fundamentally cooling down? Was it changing its overall shape?
And what was the final verdict? Because I remember hearing later that was it just dust?
It was effectively a very dusty burp. The subsequent research and imaging indicate it was a massive surface mass ejection, or SME.
What does that mean in plain English?
Essentially, the star regurgitated a huge, super-hot bubble of plasma from its interior. As that gas moved away from the star's surface into the cold vacuum of space, it rapidly cooled down. And when gas that is heavily rich in heavy elements like silicon and carbon cools, it condenses into opaque, solid dust grains.
So the star literally hid itself behind a massive cloud of its own soot.
Exactly. And combined with a cold spot on the surface, which is just a giant convection cell that had temporarily cooled down, this massive dust cloud blocked a significant amount of the star's visible light from our specific line of sight on Earth.
So it wasn't the death rattle.
No, it was just the star being a very messy eater in its old age, effectively.
But it is dying, right? I mean, even if the dimming wasn't the immediate end, the end is coming.
Oh, absolutely. Betelgeuse has moved off what we call the main sequence. In stellar evolution terms, that means it has completely run out of hydrogen fuel in its core.
And hydrogen is the main fuel for stars.
Right. A star is essentially a continuous billion-year balanced equation. You have the crushing force of gravity pulling everything inward, trying to crush the star's mass into a single point. And you have the immense energy from nuclear fusion in the core, pushing everything outward.
A tug of war.
A perfect tug of war.
Yeah.
As long as you have nuclear fuel, the engine keeps running, the outward thermal pressure stays high, and the star stays inflated.
But Betelgeuse is running on fumes.
It's basically burning through its retirement savings. It has burned all the hydrogen in the core. It's now forcing heavier and heavier elements to fuse just to stay alive. And this is where we get to the concept of the fusion ladder. This is the ticking cosmic clock.
Let's walk through that ladder step by step, because I think this really beautifully explains why the explosion inevitably happens. It all starts with hydrogen.
Right. Hydrogen fusion is incredibly efficient. It keeps a massive star like Betelgeuse alive and stable for roughly 8 to 10 million years. That's the long, peaceful period of its life.
Yeah.
But once the hydrogen in the core is entirely converted to helium, the fusion stops.
So gravity takes over.
Temporarily, yes. The core contracts under gravity.
Right.
As it shrinks, it heats up dramatically until it gets hot enough to start fusing that helium into carbon.
And how long does this helium burning stage last?
Only about 1 million years. Still a decent amount of time, but a tenth of the hydrogen phase. But then you run out of helium, the core shrinks again, gets even hotter, up to about 600 million degrees, and starts fusing carbon into neon.
And the time frame for that?
This stage lasts only a few thousand years.
Wow. So we've gone from millions of years to a few thousand. It's accelerating.
It accelerates wildly. The next step is neon fusion. That lasts maybe a few years.
Years.
Just years. That oxygen fusion starts. That lasts maybe a few months. Then it starts fusing silicon.
And silicon is the final step before the cliff, right?
Silicon fusion is absolutely frantic. The core temperature hits nearly 3 billion degrees Kelvin. The star is burning through its fuel at an insane, desperate rate just to generate enough outward pressure to hold back the crushing weight of its own outer layers. This silicon burning stage lasts essentially days, maybe a week at most.
Days. That is genuinely terrifying. A star that has lived continuously for 10 million years has a final, violent week of life.
And at the absolute end of that week, the silicon fuses into iron. And that, astrophysically speaking, is the iron crisis.
Why is iron the killer? What is it about iron specifically that stops the fusion engine?
It all comes down to nuclear binding energy. For all the lighter elements on the ladder, hydrogen, helium, carbon, oxygen, when you fuse their nuclei together, the resulting heavier nucleus is slightly lighter than the sum of the parts that went into it.
And that missing mass?
That missing mass is converted entirely into energy, following Einstein's E equals mc squared. That released energy is what pushes out against gravity. It's an exothermic reaction.
It gives you heat and pressure.
Right. But iron specifically, iron 56, is one of the most tightly bound, stable nuclei in the entire universe.
Yeah.
To fuse iron into anything heavier, you have to actually put energy into the reaction.
It's endothermic.
Precisely. It consumes energy rather than releasing it.
So the very moment the core turns entirely to iron, the energy output just completely shuts off.
Instantly. The outward thermal pressure that has supported the star for 10 million years simply disappears in a fraction of a second. Gravity, which has been waiting patiently this entire time, instantly wins the tug of war. The core collapses.
And when we say collapse, we're not talking about a building falling down, we're talking about relativistic speeds.
Yes. The iron core, which at this point is roughly the size of the Earth, collapses in on itself at about 23% the speed of light.
That's incredible.
That's roughly 70,000 kilometers per second. It shrinks from the size of the Earth to a dense ball of neutrons about 20 kilometers across in literally a fraction of a second.
And this brings us to the Chandrasekhar limit, right? I saw that referenced heavily in the Lumen learning notes.
It's a crucial concept here. The only thing holding the core up just before the absolute collapse is something called electron degeneracy pressure.
How would you explain that to someone without a physics degree?
It's basically a quantum mechanical effect. Electrons are particles called fermions, and the Pauli exclusion principle dictates they simply refuse to occupy the exact same quantum state or physical space.
Yeah.
They push back against being squeezed too tightly.
So they hold the core up.
Right. But once the mass of that iron core exceeds about 1.4 times the mass of our sun, which is the Chandrasekhar limit gravity, becomes so overwhelmingly strong that it overcomes even that fundamental quantum pressure. The electrons are literally crushed directly into the protons.
And that merger creates the neutrons.
Right. Protons plus electrons get squeezed together to equal neutrons plus neutrinos. The entire core becomes a rigid, ultra-dense ball of pure nuclear matter.
Like a giant atomic nucleus.
Exactly. It literally cannot get any denser. It becomes hard as a rock, figuratively speaking. Meanwhile, the outer material of the star is still falling inward at supersonic speeds. It violently slams into this new, unyielding neutron wall and bounces.
The bounce, the birth of the shock wave.
It's a literal physical rebound. Imagine dropping a heavy basketball and a light tennis ball stacked directly on top of each other.
Right, I've seen that demonstration.
The heavy bottom ball hits the ground and bounces up, transferring its massive momentum to the smaller tennis ball, which rockets upward at a huge velocity. That's the shockwave beginning its journey outward.
But I've read in the Astronomy magazine source that the shockwave sometimes struggles. It doesn't always just blast straight out.
That's known as the shock stagnation problem. The shockwave has to fight its way outward through all that incredibly heavy, dense iron and silicon that is still falling inward. It loses energy doing that work. It can actually stall out entirely. And this is where the neutrinos come back into the story to save the day.
The ghost particles we talked about earlier?
Yes. Remember, there are 10 to the 58th of them pouring out of the center at this exact moment. Now, even though they almost never interact with matter, the density of the material trapped directly behind the stalled shockwave is so insanely high that a small fraction of them do interact.
They hit the matter.
They do. And they deposit immense thermal heat energy into the stalled shockwave. They literally reinvigorate it. They create a superheated high-pressure bubble that violently drives the explosion outward, overcoming the infalling matter.
So the neutrinos are basically the spark plug for the whole explosion.
They are the engine, the spark plug, and the fuel. Without the neutrinos transferring that energy, the star might just collapse quietly into a black hole with a relative whimper. With them, you get the supernova.
And the sheer energy release. I've seen the figure 10 to the 44th joules in the literature, or sometimes they use the term 100 pho.
Right, a pho is a unit astrophysicists use specifically for this. It stands for 10 to the power of 51 ergs. To put that massive number in perspective, our sun will radiate a certain total amount of energy over its entire 10 billion year active lifespan.
Okay.
A single supernova releases roughly 100 times that total solar lifetime amount in just a few seconds.
That is just, it's really hard to process that level of violence.
It is. And as we mentioned earlier, 99% of that unimaginable energy is carried away invisibly by the neutrinos. Only 1% is the kinetic energy of the exploding gas. And the visible light, the blinding spectacle we would see in the sky, is just 0.01% of the total energy.
So let's think about that 0.01%, because even a tiny fraction of a percent of a supernova is brighter than billions of normal stars combined. We've had the underground neutrino alert. We've waited those agonizing few hours. The shockwave breaks out. What does the average viewer standing on Earth actually see happen to Betelgeuse?
It would likely rise very, very quickly in the sky. Within a few days of the initial breakout, it would reach its absolute peak brightness. For a type IIP supernova, which is what we expect here, it hits what's known as the light curve plateau.
And how bright are we talking at that plateau? Are we talking Venus bright?
Brighter, significantly brighter. The broad consensus from the sources, including the detailed Astronomy magazine analysis, is that it would easily rival a half-moon. And some of the higher estimates suggest it could even approach the brightness of the full moon, reaching a magnitude of -10 or -11.
A full moon, but completely concentrated into a single microscopic point of light.
That is a crucial, crucial distinction. The moon is a disk. It's about half a degree wide in the sky. It spreads its reflected light out. A supernova is a point source. It would be incredibly piercing.
It would hurt to look at.
It would look like an intense laser pointer aimed directly at your eye from deep space.
Would it be bright enough to cast shadows?
Absolutely.
Yeah.
Sharp, crisp, completely unnatural shadows at night. You can easily read a book by it. It would change the fundamental nature of the night sky entirely. If you were out in the country, away from city lights, the landscape would be bathed in this strange, stark, bluish-white twilight. It would feel very eerie.
And what about during the day? Could we see it?
It would be clearly visible. You would look up into the bright blue daytime sky, and there would be a distinct, brilliant white pinprick of light visible to the completely naked eye. It would look like a daytime star.
That feels almost medieval. It feels like an omen or a portent.
It really harkens back to the famous supernova of 1054, which created the Crab Nebula. Chinese astronomers meticulously recorded it as a guest star. It was visible during the broad daylight for 23 consecutive days.
Wow.
Betelgeuse would likely be very similar, perhaps even brighter due to proximity. It would stay visible during the day for several weeks, maybe even months.
And at night, how long does the show last?
It would completely dominate the night sky for many months. Slowly, over the course of a year or perhaps slightly more, it would begin to fade. It would shift from that brilliant, piercing blue-white, slowly reddening as the ejected gas expands and cools, eventually fading entirely below naked eye visibility.
So Orion literally loses his shoulder?
Permanently. The constellation that human beings have looked at and mythologized for tens of thousands of years physically changes forever. Future generations of humans would look up and see a completely different figure. Orion the Hunter, arguably the most globally recognizable constellation, would be amputated.
That brings up the psychological impact, which I want to get to. But first, I want to double-click on the danger aspect again, just to be absolutely thorough. We established we aren't in the kill zone for extinction, but are there literally any physical effects on Earth? You mentioned the ozone layer earlier.
Right. There is an excellent paper on RCIV by Mellett and Thomas that looked at this exact atmospheric chemistry specifically.
Great.
While we aren't close enough for biosphere sterilization, the high-energy radiation does technically arrive. Eventually.
What kind of radiation are we talking about here?
Well, you have the initial flash of light and X-rays. But later, potentially decades or centuries later, you have the arrival of the cosmic rays. These are high-energy protons and atomic nuclei, moving at near the speed of light, accelerated by the expanding shock wave.
And what happens when those finally hit our upper atmosphere?
They cause intense atmospheric ionization. They literally strip electrons off atoms in the stratosphere. This triggers chemical reactions that create nitrogen oxides, often referred to as non-ox. And these specific compounds act as powerful catalysts to break down atmospheric ozone.
Kind of like how the CFCs and old aerosols and refrigerants used to.
A similar conceptual mechanism, yes, though different specific chemistry. The model suggests that a supernova at a distance of 50 light-years would severely deplete the global ozone by 40 to 50%.
Which would be catastrophic.
Yes, but at Betelgeuse's actual distance of over 600 light-years, the effect is entirely negligible. The models show maybe a fraction of a percent of ozone depletion. It would be completely lost in the noise of the Earth's natural atmospheric variation.
Okay, good. What about the weather? I read something in the sources about an increase in lightning.
That's a truly fascinating theoretical side effect. The increased ionization in the lower atmosphere caused by the cosmic ray showers actually makes the air slightly more conductive. It creates easier paths for electrical discharge. So theoretically, we might see a measurable global increase in cloud-to-ground lightning strikes for a period of time.
So the global weather might get a little wilder. More thunderstorms.
Potentially, yes. And furthermore, those cosmic rays impacting the upper atmosphere produce showers of secondary particles, specifically muons.
What are muons?
They are essentially heavier, short-lived cousins of electrons. They shower down to the surface all the time naturally, but the flux of muons at the surface would noticeably increase.
Is that dangerous to us? Like, do I need to wear a lead hat or stay indoors?
No, absolutely not. Not anywhere near radiation sickness levels. It's a very slight increase to the background radiation we already live with. It might slightly, incredibly slightly, increase the long-term genetic mutation rate in cells over generations. But again, we aren't talking about people dropping dead in the streets.
Life is used to this.
Exactly. Life on Earth evolved in a galactic environment where this happens every few million years. The biosphere is remarkably resilient.
What about our technology, though? We constantly worry about solar flares knocking out the power grid or frying satellites. Would a supernova electromagnetic pulse do that?
It's highly possible it could cause disruptions. The initial pulse of X-rays and gamma rays and the much later wave of charged cosmic rays could certainly interfere with sensitive electronics in orbit.
Because they don't have the atmosphere to protect them.
Right. Satellites outside the thick protection of Earth's atmosphere would be the most vulnerable. We might see software glitches, temporary data loss, maybe even some permanent hardware degradation on older, less shielded satellites. But our atmosphere protects us down here on the ground incredibly well. The power grid is generally safe from a distant supernova.
So the ultimate conclusion is that it's perfectly safe to just pull up a lawn chair and watch from the backyard. No need for an underground bunker.
No bunker required whatsoever. In fact, if you hid in a bunker out of fear, you'd be missing literally the greatest astronomical show in recorded human history.
Now let's talk about what gets left behind in space. The star violently explodes, a massive outer layers are blasted outward into the interstellar void. What happens to that ultra-dense iron core that collapsed?
This is actually a bit of a very active debate in the astrophysical community right now. It depends immensely on the precise mass of the progenitor star at the exact moment of core collapse.
And as we said, Betelgeuse is estimated at about 15 to 20 solar masses currently.
Correct. And the deeply technical sources we reviewed, specifically the discussions on the Stack Exchange Astrophysics forums referencing advanced evolutionary models, suggest that for a star of this specific mass range, the resulting remnant is most likely a neutron star.
Explain why it wouldn't just become a black hole. I feel like in popular culture, everyone assumes giant star automatically equals black hole.
It's a very common misconception. To get a black hole directly from a core collapse, you generally need a significantly more massive progenitor star, closer to 25 or 30 solar masses or more.
Okay.
Or you need a scenario called a failed supernova. That's where the explosion mechanism isn't quite strong enough to fully eject the heavy outer layers, and all that massive envelope of gas falls back down onto the newly formed neutron star.
And the extra weight crushes it.
Exactly. The fallback mass pushes the neutron star over its own mass limit, and it collapses further into a black hole.
But for Betelgeuse, the current computer models strongly favor the explosion being fully successful.
Yes, the models suggest it will blow the outer layers off cleanly and successfully, leaving behind that city-sized ball of neutrons we talked about, a neutron star. It might even be a pulsar.
Which is a spinning neutron star.
Right. Highly magnetized, spinning hundreds of times a second, beaming intense beams of radio waves across the galaxy like a lighthouse.
And surrounding that newly born pulsar, we'd have the nebula.
The expanding debris field from the explosion. Over thousands and tens of thousands of years, it forms a gorgeous, complex supernova remnant. Think of the famous images of the Crab Nebula or the Veil Nebula.
But this one would be much, much closer to us.
It would. At first, it's just a blindingly bright point of light. But as it expands outward into space over the centuries, it would become a prime, stunning target for even basic amateur telescopes. A vast, glowing, incredibly complex cloud of heavy elements.
And this directly connects to the idea of cosmic recycling. I think this is honestly the most poetic and profound part of the science we're discussing today.
It truly is the beautiful part of the physics. The explosion isn't just an act of cosmic destruction, it's an act of profound synthesis. During the main life of the star, it steadily made elements like carbon, oxygen, nitrogen.
The lighter stuff.
Right. But in the incredibly violent heat and pressure of the supernova explosion itself, a completely distinct process happens called explosive nucleosynthesis, specifically a mechanism called the R process, which stands for rapid neutron capture.
This is where we finally get the really heavy stuff.
This is exactly where you get the heavy stuff. The gold in your wedding ring, the silver, the uranium sitting in our nuclear power plants, the iodine in your thyroid gland that regulates your metabolism. These elements cannot be formed in normal stellar fusion. They are forged entirely in the blinding shock wave of a dying star.
And then blasted out into the galaxy.
Yes, the explosion aggressively seeds the local interstellar medium with this newly enriched material.
So Betelgeuse dies, and in his death throes, it sprays our local arm of the galaxy with the raw chemical ingredients for future solar systems and future rocky planets.
Precisely. The solar system we live in right now, the Earth, the rocks outside, the iron in your blood, the calcium in your bones, we are basically a condensed collection of cooled debris from ancient supernovae that went off billions of years ago.
We are stardust.
We are, quite literally and scientifically, stardust. Betelgeuse is simply preparing to continue that exact cycle. It's a funeral that physically feeds the deep future of the galaxy.
That is just such a humbling thought to sit with. But it leads me to a question about probability. Why does it feel like we are constantly overdue for this to happen? I feel like I always hear that supernovae are rare, but shouldn't we have seen one close by in recent history?
We are actually mathematically a bit overdue for a highly visible one in our own galaxy. In a spiral galaxy the size and mass of the Milky Way, we statically expect a core collapse supernova roughly every 50 years.
So about 2 to 3 per century?
Exactly.
But the last one we clearly saw with the naked eye in our galaxy was Kepler supernova, right?
Yes, the supernova of 1604. Johannes Kepler meticulously observed and documented it. That was well over 400 years ago.
So where have they all been? Are the statistical models just wrong?
No, the statistical models are very likely correct. The explosions absolutely are happening. But you have to remember the structure of the Milky Way. It is essentially a giant flat pancake. It's a disk, and it is incredibly full of thick, opaque interstellar dust.
And we are stuck right inside the pancake.
We are embedded right in the middle of it. If a massive star explodes on the exact opposite side of the galaxy, say 50,000 light years away, the dense dust lanes completely block the visible light from reaching us.
So we miss the show completely.
Visually, yes.
Yeah.
We might still detect the radio waves or the high-energy X-rays like in the case of Cassiopeia A, which exploded around 1680 but was entirely invisible to the naked eye because of dust, but we don't get the spectacular light show.
But Betelgeuse is different. Betelgeuse is relatively close, just over 600 light years, and it's positioned out of the thickest part of the galactic dust.
Right. We have a very clear, unobstructed line of sight to it. That's exactly why it's such a prime candidate for observation.
Oh, that's it.
Now, we did see Supernova 1987A, which was incredibly important.
But that wasn't in our galaxy.
Correct. It was in the Large Magellanic Cloud, which is a small satellite galaxy orbiting ours. That was a monumental deal for science because it was the very first time we successfully detected those precursor neutrinos we talked about.
Oh, really?
Yes. We captured 19 neutrinos from 1987A. It perfectly confirmed our theoretical models of core collapse. But because it was 168,000 light years away, it wasn't a blinding daytime star like Betelgeuse would be.
So bringing it back to Betelgeuse, the big million-dollar question, when? Are we realistically looking at tonight, next week, or are we just totally getting our hopes up for nothing?
I have to be the bearer of bad news here.
Yeah.
Tonight is astronomically, statistically unlikely. The consensus from all the sources is incredibly clear. The predictive window is sometime within the next 100,000 years.
100,000 years? I mean, that feels like a massive cop-out from the astronomical community.
I know it sounds like a long time to us. But you have to remember to think in stellar terms. That is the blink of a cosmic eye. Betelgeuse is roughly 8 to 10 million years old. 100,000 years is roughly the final 1% of its entire lifespan.
So it really is at the very end.
It is entirely at death's door. We just don't know if it's currently knocking on the door or just walking down the hallway toward it.
But why can't we know for sure? Can't we just point a massive spectrometer at the star and see exactly if it's currently burning carbon or if it's reached the silicon stage?
We can't see the core. That's the fundamental observational problem. We can only ever observe the outermost surface layers, the photosphere.
And the surface doesn't tell us what the core is doing?
Not precisely. There is a massive disconnect. The Great Dimming showed us that the surface is incredibly dynamic and active, but that surface activity doesn't definitively tell us if the core is currently burning carbon or neon. If the core is actively burning silicon right now, it literally has days left. But if it's only burning carbon, it has 1,000 years left. The neutrino burst is the single only thing that will tell us the core has finally failed, and by the very time we see those neutrinos, the collapse is already happening.
So the Great Dimming was definitely not a countdown clock.
No, it wasn't. In fact, the Universe Today source explicitly notes that the star is currently recovering from that disruptive event. It's steadily returning to its normal, semi-regular pulsation cycle. So probably not tonight. But, and this is the beauty of probability, it technically could be tonight. We just don't know.
If it did happen tonight, or in our lifetime, the cultural impact would just be massive. I think about how much we, as a species, subconsciously rely on the absolute stability of the night sky.
We absolutely do. We take the concept of the fixed stars completely for granted. To see one of the brightest, most famous stars fundamentally change so violently would deeply shake us.
It would dominate every news cycle for years.
It would be a profoundly unifying global event. I imagine almost everyone on Earth, in the northern hemisphere, the southern hemisphere, stepping outside of their homes, standing in the street, to collectively look up at the exact same thing.
No subscription fee required, just look up.
Exactly. Though it would also be a massive headache for professional astronomers.
Oh, how so? I would think they'd be thrilled.
They'd be thrilled about the supernova, yes. But general optical astronomy would be severely disrupted. The night sky would be far too bright.
Oh, because of the glare.
Right. Deep sky imaging requires incredibly dark skies to capture faint galaxies. Having a second moon's worth of light pollution emanating from a fixed point in Orion would wash out a lot of sensitive observations for months.
That's a funny side effect. What about animals?
That's a real concern. Nocturnal wildlife would face navigational confusion.
Like migrating birds or insects?
Exactly. We already see terrible disruption with artificial city lights. Imagine introducing a massive new light source that casts deep shadows and moves across the sky differently than the moon does. It would definitely confuse biological rhythms and navigational instincts for a season.
But for humanity, I think it would be a moment of profound connection.
I agree completely. It intimately reminds us of our true scale in the universe. We're incredibly small observers on a tiny rocky world, watching a massive nuclear furnace 700 light years away violently destroy itself.
And there is that mind-bending time delay we talked about earlier. We talked about distance. If we see it explode tonight, it didn't actually happen tonight.
No. Because of the speed of light, if we see the flash tonight, the actual physical explosion happened roughly 700 years ago.
Wow.
It happened while the late medieval period was in full swing here on Earth, while the Mongol Empire was fracturing, while Dante was writing the Divine Comedy. The light has just been traveling across the empty void for 7 centuries, and we are just now getting the news.
That is always the trippiest part of astronomy for me. Every time we look up, we are literally looking backward into the past.
We're essentially archaeologists of light.
So to begin wrapping this deep dive up, we've covered the invisible neutrino burst, the violent shockwave breakout, the daytime brightness, the safety of our atmosphere, and the deep nuclear science of why it happens.
We have thoroughly covered the life and death of a supergiant.
If you had to summarize the ultimate take-home message for our listener who is maybe stepping outside tonight hoping to see this, what is the core takeaway?
I would simply say be patient, but be prepared to be completely awestruck. Betelgeuse is a cosmic ticking clock. Whether it goes off in our lifetime or 10,000 years from now, long after we are gone, it is an absolute inevitability.
The physics demands it.
The physics demands it. Gravity always eventually wins, and when it finally does, it won't be a disaster for Earth. It will be the ultimate, grandest demonstration of how our universe functionally works. It inherently destroys to create.
It's not just a death.
No, it is a profound transformation. When Betelgeuse finally explodes, it will not mark destruction, but creation. It is a powerful reminder that even in the utter violence of stellar death, the universe is actively forging the atomic elements of future worlds.
And on that profound note, we are going to sign off. But do me a favor. Tonight, if the sky is clear where you are, step outside. Find Orion. Look up at that glowing red star on the left shoulder. And just appreciate it while it is still there, because one day, maybe tonight, maybe in a millennium, it is going to put on the greatest show this galaxy has seen in 400 years.
And keep an eye on your newsfeed for those SNUWS neutrino alerts.
Absolutely. Thanks for diving deep with us today. We'll catch you on the next deep dive.
Clear skies, everyone.